I want to do a quick, hopefully quick, video on inverse functions. Now, this is section 5.3 in your textbook. So, an inverse function is labeled as, it's got a little -1 as an exponent here. That would indicate the inverse. Now, what an inverse is really all you do is you reverse or you switch your x and y values. That's really all it is. In terms of the picture or the graph, we've talked about reflections in x-axis, we've talked about reflections in y-axis before. This is actually an inverse. When you draw the picture, actually ends up being a reflection in what is referred to as the y is equal to x-axis. The y is equal to x-axis. Think about what y is equal to x means. So that means, like, if your x is 0, your y is 0. If your x is 1, your y is 1, right? Because they're equal. If your x is 2, your y is 2. And so this diagonal line is your y is equal to x-axis. So for example number 1 in your textbook, they actually give you a set of ordered pairs. They give you -2 and -8, 0 and -2, 3 and 4, and 4 and 7. And they ask you just to plot those onto your graph. So again, I'm just going to sketch it really quick. If you were to do -2, 1, 2, and -8, let's say 1, 2, 3, 4, 5, 6, 7, 8. That's going to be like, I don't know, right about here. 0 and -2 is going to be like right about here somewhere. 3 and 4 would be 1, 2, 3, and 1, 2, 3, 4 would be right about here. And 4 and 7 would be like 4, and that would be 4, 5, 6, 7. So I don't know, right about there somewhere. So it's not like a graph where you're going to draw a line. This is just a set of ordered pairs. It's just a bunch of dots. It's a scatter plot. But then they want you to do the inverse. So the inverse of this is literally you flip your x's and your y's. So for the inverse, you're going to have -8 and -2 because I just flipped where my x's and my y's were. You're going to have -2 and 0 because I just flipped. You're going to have 4 and 3, and you're going to have 7 and 4. So if I put those on the graph, -8, so 1, 2, 3, 4, 5, 6, 7, 8, let's say I'm 1, 2. And -2 and 0, say that's right about there somewhere. 4 and 3 would be like 4 and 1, 2, 3, it'd be like here somewhere. And 7 and 4 would be like 7, let's say that's here, and 1, 2, 3, 4, it'd be like here. Now, if you can picture this, if you were able to fold this graph along that y is equal to x-axis, what would happen is this red dot would fold over to touch that black dot. Same thing here, same thing here, and same thing here. When you fold along that y is equal to x-axis, those dots are going to basically meet up. They're going to touch one another when you fold the paper on the diagonal like that. So in terms of a picture, that's what happens. Now, in terms of an equation, because most of the time you're not getting a set of ordered pairs, they're giving you an equation. So if we look at something like example number 2, and black again. If we look at example number 2, they give you f at x is equal to 3x minus 4. Well, when you have f at x, that's just function notation. Function notation is just a short way of writing an equation because that tells you, yes, this is a function and the unknown value is x. So f at x and y basically are interchangeable in this situation. So we have y is equal to 3x minus 4. Now they ask for the inverse. So remember that the inverse is literally you flip your x and your y. So where you have a y, you put an x, and where you have an x, you put a y. And then, because you never leave things in terms of x, you always leave it in terms of y, that means that you isolate your y value. So I will add 4 to this side to get rid of it. So I'll add 4 to this side. So I have x plus 4 is equal to 3y. And then I will divide this side by 3, and I will divide this side by 3, and I end up with y is x plus 4 over 3. So this is the inverse of this. Now, what I want you to notice is you are doing exactly the opposite or the reverse of what you were doing. I was in the original subtracting by 4, now I'm adding by 4. I was multiplying by 3, now I'm dividing by 3. And so the inverse, you end up doing exactly the reverse of what you were doing in the first one. So if you want to know if two equations are inverses of one another. So if I gave you, and I'm doing example 3, but I'm doing example 3b first, and then I'll go back to A because I want to show you something. If they tell you that f at x, so the first equation is 2x minus 5, and g at x, so the second equation, is x plus 5 over 2. I have a dog trying to break into my room here. And I want to know whether those are inverses of one another. First of all, with simple ones like this, I can tell just by looking at it, because if I'm doing exactly the reverse of what I was doing in the first equation, then they are. So I was subtracting 5, I'm adding 5. I was multiplying by 2, I'm dividing by 2. I'm pretty sure that these are inverses of one another. But of course, in math, pretty sure is not good enough. They want you to prove it. To prove that two things are inverses of one another, you do composite functions. You do f of g at x, and then you reverse it and do g of f at x. If when you do both of these composite functions, you end up with an answer of x in both situations, then you can say, yes, these two are inverses of one another because I've proven it mathematically. So really quickly, if we do this, so f of g means we take the f function, which is 2 times a variable minus 5. But the variable is x. What am I replacing x with? I'm replacing x with g at x, which is x plus 5 over 2. Now, if I simplify that, these 2's will cancel, and I have x plus 5 minus 5, which is just x. So it worked for f of g. But just because it works for one doesn't mean it'll work for the other one. So yes, I still have to do the other way. So g of f. So g is some variable plus 5 over 2. Now, what do I put in place of that variable? I put the f at x equation, which is 2x minus 5. So this time on the top, I have minus 5 plus 5, which leaves me with 2x on the top and a 2 on the bottom. Those 2's will cancel, and I get x. So because I have x for both scenarios, yes, these two equations are inverses of one another. Now I want to go back to A, because for part A of that example, f at x is 2x minus 7, and g at x is 7x plus 2. Again, I can look at that and be fairly confident in my answer, because if I'm subtracting 7, I should be adding 7 over here, and I'm not. So I already know ahead of time these likely are not inverses of one another. So, but I have to prove it. So first I'm going to do f of g. So again, f of g means take my f equation, which is 2 times some variable minus 7. The variable is g at x, which is 7x plus 2. So this is 14x plus 4 minus 7. So this is 14x minus 3. Well, that's not x. So because this one didn't work out to be x, I don't even need to bother to do g of f. I can just, with confidence, say no, those are not inverses of one another. Okay. Example number 4. Example number 4 says, is the inverse of y is equal to 4x plus 3, is it a function? Okay, well, first off, I know that this is a function because if the x has an exponent of 1 on it, it is x to the first. That is automatically a linear function, meaning this is a straight line when I draw it. Again, if I wanted to draw it, 4x plus 3, this is in mx plus b form, so 3 would be my y-intercept, 1, 2, 3. And then 4 over 1 is my slope, and slope is rise over run, so I could go up 4, 1, 2, 3, 4, and go across 1, and it's a fairly steep line going this way. That is a function because it passes the vertical line test. Remember, the vertical line test says if I can draw a vertical line anywhere and it only passes through the graph once, then yes, it's a function. So this is a function. A line is a function. So it asks, so is the inverse of that a function? Well, the first thing then I would have to do is I would have to find the inverse. So the inverse, I would flip my x and my y. X is equal to 4y plus 3. I'd subtract 3 on both sides. And then I would divide by 4. So I would have x minus 3 over 4. Now, if I graph that, again, because the highest exponent on the x is a 1, I know that this is a linear function. I know this is going to be just a straight line. So it likely is a function. But if I wanted to prove it and graph it, I don't like it looking like this to graph it, but I could write this as 1/4 x minus 3 over 4, right? The 4 is a common denominator, so I just put it on the bottom. So again, my y-intercept would be negative 3 over 4, so down 3/4 of a square. So let's say there. And my slope is rise over run, so it would be go up 1 and go across 4. 1, 2, 3, 4. So it would be about here. Again, think about that y is equal to x-axis. This is actually a reflection across that. This point would fold down to meet this point, and so on and so on and so on. So again, it's a straight line. It's a line. It passes the vertical line test because it doesn't matter where I draw a vertical line. It doesn't matter where I draw it. It only goes through the graph in one spot. Here it goes through here. Here it goes through here. Here it goes through here. So yes, it is a function. If you have a linear equation, something that's going to create a straight line, the inverse is also going to be a function. But that's not always the case with all graphs, that if the first graph is a function, so is the inverse. That's not always true, which leads me to example number 5. So example number 5 talks about f at x, or if you want y, is x squared minus 1. So the first thing it wants us to do with that is it wants us, oh man, that was a horrible line. The first thing it wants us to do is it wants us to graph that. So if I can do any better on my straight lines here. Remember, x squared is a parabola. -1 means it's been moved down 1. So my vertex would be 0 and -1. And then it would go something like this. Now, they just asked us to sketch it. So like, as long as you get the vertex right and then, give me a parabola, I'm pretty much a happy girl. So when it asks us to graph this, it wants to know what is the domain of this and what is the range of this. Now, I get this question a lot. I get domain and range confused. I don't know what to put. I don't know how to find it. So domain. Domain always is talking about your x values. So x values are left to right. Really, you're going on the assumption that x can be anything. And what you need to look at is that true? Can x be anything? Is there any restrictions here? Well, no, it appears that it's going to keep on heading to the right because as it goes up, it's also heading off to the right a little bit, and it goes to the left forever. So really, x appears to be anything. No restrictions, no problems, no nothing. So range talks about y values, so up and down. And so when we talk about range, again, I start with the assumption, okay, can y just be anything? Is that the answer? Y is any real number. Is that the answer? Well, when I look up, that appears to be true because it goes up forever. Look, it's going up forever. It's going up forever. So there's no restriction on it going up. But when I look down, it reaches a bottom point, a point at which it goes no lower. And that is at -1. So there actually is a restriction, and that restriction is that y has to be greater than or equal to -1. That's my restriction. That's all they want. Okay, so that is my range. So then they want me to graph the inverse. So the first thing I have to do is find the inverse. So flip my x and my y's, move the 1 over, and I have x plus 1 is equal to y squared. But I don't want y squared, I want just y, which means I have to take the square root of this side, which means I have to take the square root of this side. So it's really plus or minus the square root of x plus 1. Because they didn't tell me this has to be a function or anything like that, so I don't really know. Now, if I'm going to graph that, remember that this is a reflection in the y is equal to x axis. So I'm going to take my vertex here, and I'm going to switch my x and my y. So -1 and 0. So -1 and 0 turns out to be right there. And again, I'm going to just flip that sideways. So it's actually going to do this. Now the question is this a function? And the answer is no, it's not a function, because if I do the vertical line test, this vertical line passes through the graph in 2 places. There is more than one answer for any x value. So for instance, if my x value was 3, I would have the square root of 3 plus 1. So I would have the square root of 4. Well, that would actually be plus or minus 2. That's 2 answers. If there's more than one answer when you put in a specific x value, then it's not a function. Okay, so the other thing it wants us to talk about is it wants us to talk about domain, and it wants us to talk about range. So again, let's think about domain and range. So domain is x values, so we're looking left and right. And it looks like it's going to the right forever. However, if I look to the left, it stops right here at -1. So it's that my x has to be greater than or equal to -1. Now, what about my range, up and down? Well, I know it doesn't really look like it, but this is headed up forever, and this is headed down forever, even though it's not going down a lot over time, it is. So my answer is that y really can be anything. It can go up forever, it can go down forever. Now, what I want you to notice, what they want you to notice by doing this example, is that when you look at the original, the domain is x is any real number, the range is y is greater than or equal to 1. When you look at the inverse, it's completely reversed. The domain is x is greater than or equal to -1, and it's the range this time that it belongs to the set of any real number. So when we talk about inverse, the domain and range actually flip as well. All right. Okay. I'm skipping example number 6 because it's exactly the same as this one. And we're going to look at example number 7. And then I'm actually going to do a question from your homework as well. So this time it wants me to find the inverse of y is equal to 1 over x plus 1. So if I want to find the inverse, I need to flip my x and my y. So x is equal to 1 over y plus 1. The problem that we run into with this is that the y is in a binomial in a denominator, and that's not good. The only thing I can do with that, because I can't just take the y out of the denominator because it's part of that binomial, y plus 1. The only thing I really can do with that is multiply the whole thing by y plus 1 so that they cancel. But because I've taught you well, you know that if you do that to one side, you have to do it to the other side. Now, most people's instinct is going to be to take that x and do the distributive property here. That actually is not helpful. If you do that, you're going to get yourself kind of stuck. Remember, you're trying to get the y, so don't do that. You're trying to get the y by itself. You're trying to isolate the y. So we've made a step forward because we've got it out of a denominator. But now we have to isolate it. We have to get it alone. So the first thing I'm going to do is I'm going to divide this one by x. So I'm going to divide this one by x. So I'm going to have y plus 1 is equal to 1 over x. I want the y by itself, so I'm going to subtract by 1. So I'm going to subtract by 1. So I have 1 over x minus 1, and that is your inverse. Now, I'm going to skip the word problem just because of time here. This was supposed to be a quick video, and it's not. But I really want to go over one of the questions from the homework because it's one that most people get wrong. And I will put it on an assignment. I will put it on a test. I will put it on an exam. You will see it again. So that's why I'm going to do it. All right. And honestly, I don't remember which one I gave you for homework. So I'm just going to pick one like it. If I pick the right one, great. If I pick the wrong one, sorry. But I'm going to look at number 69, which is y is equal to 1 minus x over x plus 2. So they want the inverse of this. So I have to flip my x and my y. So x then is equal to 1 minus y over y plus 2. So the problem with this is that now you have two y's, not just one. So that's a problem. So again, just like with the last one, first off, there's a y in a binomial in a denominator. You've got a fraction there. No one wants to deal with that. So we start exactly the way I started the last question, and that is we're going to multiply this by y plus 2. So that means we're going to multiply this side by y plus 2. So we're going to have x times y plus 2 is equal to 1 minus y. Now, last time I said your instinct would be to multiply this out, but I said that's not what you want to do. Now it is what you want to do. The reason why you want to do it this time and not last time is last time you only had one y in the whole question. This time you have two y's. You've got one on this side of the equal sign and one on this side of the equal sign, and that's a problem. So what we are going to do is we're going to expand this out to be xy plus 2x equals 1 minus y. And like I just said, you've got y's on both sides of the equal sign, and that's a problem. So what I'm going to do is I'm going to move anything, any piece that has a y to one side of the equal sign, and any piece that doesn't have a y in it to the other side. So that means I'm going to take this y and move it over here. So I have xy plus y. This 2x doesn't have a y in it, so I'm going to move it over here. So I'm going to have 1 minus 2x. So what that does is it gets all your y's on one side with no fractions anywhere. So now I have xy plus y. Y is a common factor here. I can take it out as a common factor. If I take it out of xy, I just have x left. If I take the y out of here, I just have x plus 1 is equal to 1 minus 2x. So now remember, I want the y by itself. So if I divide this side by x plus 1 and I divide this side by x plus 1, I end up with, these will cancel, and I end up with y is equal to 1 minus 2x over x plus 1. This is your inverse. This catches a lot of people. So I would, in your notes, put a little star beside this one because you're going to see it again. All right. That's it for section 5.3. I will hopefully tomorrow make a video on 5.4. Okay. See you later.